Started. So, this class might be a little bit interesting. I brought lots of notes, but not the ones I need. Luckily, I have scanned copies on Dropbox, so I'll just be walking over there a lot. No exams. We'll be aiming for Tuesday, and I'll let you know when we're closer. But either Tuesday, I mean, if we're returning the exams Tuesday, then we won't do this. It'll be Thursday, but either Tuesday or Thursday, I would suggest, but you don't have to, but bring a laptop, because we're going to start talking about, and theoretically you guys have already done this, but I'll show you guys in Excel how to solve differential equations numerically using the Euler method. Very simple, doesn't take any time at all. I'm not even going to bring in, the Excel book that I'm starting with will be blank, just to emphasize how quick this is to set these things up. And we'll do one of the homework problems that was assigned. So I think it's the only one on there that says use Excel, but we'll start that. We won't finish it, but we'll start that homework problem so that everybody has seen at least once how do you numerically solve a differential equation for a non-isothermal reactor in Excel. And I'll send out the spreadsheet after that, after we do that. Yeah?
What exam grade is posted on campus before we get the exam?
I don't know. I mean, they can be. Does it? I don't know if it really makes a big difference one way or the other. That's actually a logistical question I have. In a class this size, how do people normally return exams to you?
Mailbox.
Even though you guys don't have individual mailboxes, I'm not violating some rule.
When we get a mailbox, we sign a paper.
We sign a paper
That says, as long as it's in the mailbox, you give up your right to privacy. All right, you guys signed it, huh? Okay, so that's the plan then, is I'll let you know before Tuesday if you can expect them to be in there Tuesday morning. If not, then try to bring a laptop Tuesday. Again, you don't have to, but if it helps you to work through it as I'm doing it on the, on this computer, you guys can do it on your own. If it doesn't help you, then save your back some trouble. So any other questions? Okay. So where we left off was this sort of curve. So what is this curve? What did I just plot?
Equilibrium curve.
Right. This is the entire curve is the equilibrium conversion. There was a little bit of confusion at the end of the last period. Some people walked up and they were like, is this the equilibrium conversion? No, it's just this curve gives you the value of the equilibrium conversion, which of course changes with temperature because all reactions are either exothermic or endothermic, and so that's what leads to temperature having an impact on the equilibrium. We use this example for an endothermic reaction. You have to add heat. So adding heat by increasing the temperature shifts your equilibrium to the right. Now this is obviously not an endothermic example because as I'm increasing temperature, the equilibrium conversion is decreasing. So the one that I just drew is for, this is an exothermic, and then an endothermic one will look very similar. but be going in the opposite direction. So if I have an adiabatic reaction that starts here, where does it end up? To the right. What's the style of that curve? Is it a straight line? What's the slope? We haven't talked about that, but what's the slope related to? Right. So it's not exactly, but the slope is proportional to negative times the delta H of reaction. Negative because, again, this is an exothermic reaction, that's a positive slope, right? So negative and negative, you get a positive value. And again, there are formulas where you can just calculate this, but it's not directly equal to, but it is related to those things. And that's where it stops. Of course, the equation that you get continues. It doesn't say anything in there about stopping at xe. And what's the equation that you get is right? So what did we use to derive that equation? What assumptions have we made, or what has to be true about the system for this equation to work? Adiabatic. Steady state. No shaft work. Anything else?
Single reaction.
Yeah, because we have 1x, so no phase change. Seems like a lot, doesn't it?
Closed system.
Closed system, yeah, I mean, this is a flow system, so I don't know if we...
Well, because you can't be losing the product like a fusion reaction, like a membrane reaction.
Oh, right. No, it's not a membrane reactor. That is true. Yeah. Couple other little things is that the heat capacities that we put in there, right, you're going to be usually given those. But again, a lot of times, especially from a book problem, he's not going to put the little hats on there. Okay? Just don't let that throw you off. If you're given a heat capacity, ignore the fact that you know and I know and hopefully everyone in chemical engineering knows that those are actually dependent upon temperature. Just throw that out of your mind. That's pretty much it. So, I mean, one thing that I want to point out, this isn't specific to a PFR or a CSTR, right? Either one will work just fine. We've been focusing the last couple of lectures on CSTRs because they give nice, simple analytical solutions. There's no differential equations. Again, starting with when you guys are suggested to bring your laptops, we're going to start with a PFR. So then you're going to have a differential equation that you can't solve. You guys certainly at this point should know how to set it up, but you won't be able to solve it without using some sort of computational assistance, be it MATLAB, VBA, Excel, I don't care what you use. I'm going to show you how to do it in Excel. And if you want to use Polymath, that's fine with me too, but I think Excel is more valuable because when you all leave here, I promise you're going to use Excel. I don't think you're ever going to see Polymath again. So, you know. Okay, and like we said, this is the maximum conversion that we can achieve, right? Unless we do what? Yeah, I can not run it adiabatically. So if I ran it isothermally, what would it look like? Yeah, exactly. It's just a straight line. That's pretty easy. Now, are the only two options adiabatic or isothermal? Right, but even if I'm talking about just a heat exchange PFR, I don't have to run it isothermally. right? There are in-betweens. I can either run it isothermally, and you're going to have a lot of problems like that, where you're going to be asked to find what's the flow rate of the cooling fluid that you need. You know, given this heat transport coefficient, what's the flow rate of the cooling fluid you need in order to keep the system isothermal? But you could run it somewhere in between, of course. And yeah, like Adam said, another option that you have is you can design a reactor that maybe goes here. You don't want to go all the way to equilibrium, because I think it was pointed out a couple lectures ago that often requires a very, very big reactor, right? And so maybe you go to 95% of equilibrium, and then you cool it. Maybe you go right back to T0, and then in a second stage, you react it again, you cool it, react it, cool it, react it. And I'm not drawing this very well, but all of the slopes should be the same, because that's just dependent upon the heat of reaction. All right, so let's do an example now where we calculate, just for a single stage, the equilibrium conversion, and we'll call this the equilibrium temperature as well. All right, so I'm going to do a lot of erasing because I'm going to try to stay on this side of the board so I can read that on the screen. So just shout if you're still writing something down when I start erasing it. Okay, so if we have A goes to B in a PFR, and the delta H of reaction